Good morning, everyone, and thanks to Rajan and Pratim and the organizers of this workshop for the invitation. I'm going to talk about something very different. I'm going to talk about some of the large-scale simulations that we are doing in our laboratory and in collaboration with our experimental group of Chris Sorensen. And we're going to talk about morphology of soot clusters. Okay, so when I started into this game in late 90s, 98, 99, something like that, it was pretty much known that soot clusters have a fractal dimensions 1.8, and it was known how they form, called diffusion limited cluster aggregation and all that. So from that point of view, at that point, there was nothing new to be done for doing simulations. But as you know, physics and science goes through these inflection points, and this was one of those. So let me give you a little bit of background where we are. Okay. There it is. So good. So there is a TM picture of soot. It's a fractal, and if you then do measurements, this is from Chris Sorensen's lab, and I call soot aggregates. Then this is where you have the mass of the cluster versus its radius, some sort of radius of gyration, and you can see that over a large orders of magnitude of mass and radius, you can see the slope of 1.8. And this is when you kind of declare, we know everything, there's no more to be done, right? And so then came an experiment in Chris's lab. This is about late 99 or early 2000s. And he's looking at, this is an upright flame. There's a reason for using that adjective. So in this upright flame, he found that if you look at the scattering intensity versus wave vector, mainly about angle, you can convert that to a wave vector to look into different length scale. He found that yes, there is this 1.8. Okay, there is this 1.8 for large values of Q, and then there is this other slope of 2.6. What could that be? And then they can characterize the clusters. This is your typical 0.5, 0.7 micron clusters, fractal dimension of about 1.8, and then these are the larger clusters, about 10 micron or so. It starts about actually 1 to 5 microns up to 10, and this seems to have a fractal dimension of 2.6. So two questions come in. One, this measurement of 2.6 from scattering intensity, is that valid? Does that give you the fractal dimension? It was not known because it has a large refractive index, and you don't know that whether this will give you the fractal dimension or not. That's one question. And the second is, what is it? What is this 2.6? So we did some large-scale simulations at that point, starting from monomers in a box, particles in a box, and then we ran the two particles come together, they form a cluster, clusters diffuse around, then they will touch another cluster and form the standard prescription of diffusion limited cluster aggregation. And we ran very large systems, a very, very sophisticated and efficient program. So we could run, at that point, we were running with about 800,000 particles. And we found a similar trend there is that there is a crossover from a fractal dimension of 2.6 to a fractal dimension of 1.8. And this crossover happens at some point we call the radius of gyration of ideal gel point. So it's not that It's not that, this is the power of simulation. It's not that we see these two slopes, but we can also point out where is this crossover taking place and what's the physical meaning of it, right? This was not known at that point. So what is the physical meaning? This is what happens in these things. This crossover point, we can estimate that by creating an ideal gel. So we have this 1.5, 1.8 diffusive clusters, and then these clusters themselves, treat them as a beach ball, and those clusters themselves will touch each other and span the whole system and will create a percolation cluster. So let me show you a picture of that. So this will be an artist's drawing, that this 1.8 clusters, this is your short length scale. And then if you go into a large length scale, over this large length scale, these clusters, these are your new beach balls, which are going to percolate. And they are going to now form this structure in a larger length scale of 2.6. 2.5, 2.55 is the fractal dimension that you get from static percolation. This is not static percolation. This is still particles and clusters are moving around and forming this gel. But if you create by hand a static percolation, then you will get a fractal dimension of 2.5. Okay, so here is another set of those drawn a little better. So again, if you look at a short length scale, large Q is inversely proportional to length. Large Q, you will see a fractal dimension of 1.8, and over a large distance, you will find a fractal dimension of 2.6. So this is a hybrid structure. Okay, so this suit is hybrid. This is not uniform 1.8, and you can actually figure out what is this crossover going to be. You can have a simple model for it, and when you do simulations, you can see that yes, very close to that, within a factor of 2 of that estimate, this crossover takes place. So the picture was pretty robust, except that it was seen in Kansas State, it was modeled in Kansas State, and that was that, right? You need other people to confirm to you, and this is how your fame spreads. And so then in the next few years we figured out that super aggregates are everywhere. It's not just in Kansas. They're everywhere. They're everywhere. They come from a turbulent pool fire from Sandia Labs. They came from Rajan's work, Rajan and his group's work, from various forest fires. And also Rajan is working on now the inverted flame. This is why I said Chris's lab, the flame was upright, this inverted flame. And he is making this super aggregates up to the wazoo. And we will need that. We'll need that. I'll come to the challenges that come in. So whenever we see something like this, you scatter light from it, you will see super aggregates. And then you can have this wildfire smoke cloud, and so all go to the atmosphere, and again, they are packed with these super aggregates. All right, so the challenges. So remember that this was about 2002, 2004, around that time. So we said, okay, we have this simple model that these DLCA clusters will percolate and will form this 2.6 cluster. We have a model. We can figure out what this crossover is. They seem to match. Very good. But we still need to characterize the super aggregates. We couldn't do it then. We didn't have enough computing power. We didn't have enough resources to study those. And so now we also know that the LCA clusters, the smaller length scale clusters, also very well. We can characterize them by a 3-parameter description. So you don't characterize just by the fractal dimension. You need to know the prefactor that goes into the fractal dimension scaling, and also you need to know the short range backing of this model. So these are the 3 parameters that come in, and that's the way you can describe the 1.8 cluster. Can we describe that for super aggregates in this kind of 3-parameter description? And also, Then the second challenge is that how do they scatter light and also absorb light, and what are the implications of this super aggregate? Okay. So we have. I'll show you some preliminary results on this from one of my other students. And so this is just to show that we are doing these large scale simulations, and again you can see this 2.5 to 1.8 crossovers. We put this factor C there. This prefactor is related to this 3-parameter scaling that I was talking about. So we can actually compute that, not just the fractal dimension. And here something very interesting happens, is that if you now look at this whole collection of your clusters from the box, you will find that this, and you plot n versus r, you will find that you will give this 1.8 scaling for smaller clusters, and with the prefactor of 1.3 or 1.4 within some error, and that's the canonical DLCA of 1.8. But the superclusters, they seem to scale with a fractal dimension of 2.5 and a very small prefactor, we call that K naught. Very, very small prefactors. And why is that? What's the importance of that? That's something that we need to understand. So let's do for a different volume fraction of these aerosols, and you find that that scaling actually moves. You still have 1.35, you still have about 1.5, and the crossover, of course, changes because this crossover depends on the volume fraction of the monomers. One can do one other thing, and this is something we haven't done before. We didn't really focus on the shape of the superclusters, super aggregates, is that we can define the beach ball, the bigger monomers, as starting here with a mass of n at that point, and what's the size r at that point. So we can rescale the whole thing in terms of these beach balls. And when you do that, all these different results will fall on one single mustard curve with a little bit of fatness, and we can have a good scaling through it. And you get now, instead of 1.35 for canonical DLCA, you get a different K naught, but not too far off. It's not like 0.1 or anything in this new scaling with the 2.5. And we can have now results from very different volume fractions all over the same scaling. And so this crossover to population scaling, we need to model that better. These are still preliminary results. And this is where we need a lot of experimental data. It's not just for one volume fraction, but for large scale of volume fractions, large set of clusters. And we need to figure out also this ideal gel point result and scale them to see what kind of prefactors that we can influence. So Rajan is planning to do a lot of experiments, or already doing some, and this kind of scaling will be very, very important. And then we can also, we are also looking at the correlation functions of these things to understand this crossover better, so I'm not going to get into that. We can see this crossover. This is actually pretty neat result. Is that if you look at the correlation function of the super aggregates, you see that there is a crossover from these two different DFs. One is that 1.8, and then you have the larger 2.5, and then you kind of hit the edge of the cluster, and there's a cutoff. So finally, we are also doing light scattering model, light scattering or absorption from these superclusters. Here I'm showing you result for a cluster with 50,000 particles. We're trying to do with up to 5 million particles of this dipole approximation. And here, when we do, this is not structure factor. This is just light scattering from the full electromagnet. And when we do that, we get this 2.5 to 1.8 crossover, which is very important because when you do a measurement in an experiment, you're not taking just the Fourier transform, you're taking the light scattering, right? So you get the same sort of result, and now you can see why that happens, even though these clusters are dense, but still, if you know how much void space they have, you can do some kind of a rescaling with the model that the overall density over the volume, then you will get that actually the overall density of the surface is not very large, and so the simple Fourier transform model actually works very well. So we confirm that, and that's very good. That means all the experiments in physics lab, Rajan's lab are actually doing correct measurement of the fractal density. This is actually very important result. And we can now look at how they absorb light, how you can decorate them, perhaps with other molecules, water molecules, and then how do they scatter light, how they absorb light with other organic molecules. So these guys are there from the coal fire, from the wildfires, and all sorts of things. And they are real, they are up there, and they are not been characterized at all, and this is a big challenge. This is where I'm going to
Thank you.